Hi. Section 30.4, the derivative as a rate of change. In this section, we'll consider some simple applications of the derivative. Particularly, we'll consider motion along a line and some examples from economics and biology. Okay, here in this definition, okay, let S as a function of t be the position of moving particle. Then here, change in S divided by change in t is the average velocity. If we make derivative for s with respect to t, then that is instantaneous velocity. And if we take absolute value, then that is the speed. If we make one more derivative for s, then that is acceleration. So acceleration is a derivative of velocity and second derivative of position. Okay, here in this example, it is showing the position, velocity, and acceleration. So it is asking which one is which. Okay, but here apparently this red one is cubic polynomial, and this cyan color one is quadratic, and yellow one is linear. So that apparently here this red one must be s, and this cyan must be velocity, and now yellow one must be acceleration. Because like here, and a is obtained from the velocity and through derivative, and velocity is gotten from the position. Okay, and now also you can check this one quite easily. Here for s, okay, this position, the derivative is 0, so that s derivative is velocity. So from this point you go down, then now here 0, that means that if this is s, then this cyan color must be velocity. And also the same here, the slope at curve of s is 0, that is exactly here now, the velocity is 0. Okay, you can find the position, the velocity, and acceleration geometrically. Okay. Here, a dynamite plus the blows a heavy rock straight up with a launch velocity of 160 feet per second, and the position s of t is given in this way after t seconds. Okay, here how high does the rock go? That means that we have to find the highest position of the rock. Of course, at the highest position, okay, let's consider this one pictorially in this way, is dynamite plus the begins moving a rock upward and go up and down like that. Now we need to find that height. So at the moment here the velocity is 0, so that we need first to get velocity. Okay, v of t equal, now s of t is given in this way, so that v of t must be 160 minus 32t. Okay, and here in highest position the velocity is 0, so we set here 0. Then we can easily see t is 5. So at time 5, t is 5, it is at highest position. So here we have s at 5, so that we want to find the height here. That is now 160 times 5 minus 16 times 25. Okay, is t squared, which is 25. Okay, here we have, so that is same as, okay, 16 is common, so first one is 50 and second one is 25, so that is 25 times 16, which is the same as 400. Okay, so 400 feet is the highest position. Okay, now part B. What are the velocity and speed of rock when it is 250 above the ground on the way up? So it is okay, this highest position 400 and here 256, somewhere around there is up and down, so that we want to find at the position here the velocity and speed. Okay, and on the way down, that is an opposite. But anyway, we'll try to find the first the velocity and speed on the way up. Okay. Okay, so here we have to find time. Then once we know the moment, then we can find, okay, velocity is already known here. Through derivative, we know. So if we know the time, then we can find the velocity. And absolute value of the velocity is the same as now the speed. So we have to find the time. The question is the moment. Okay. But here, that is when it is now 256. So that S of t, we have to solve the problem so that S of t is now 256. Okay, from this one, S of t is now 160 minus 16t squared equal 256. Okay, we try to divide by 16 and move everything to one side. Then that is t squared, and that will be minus 10t, and divided by 16 makes, that is 16. Okay, so that is 0. Okay, we have to solve this quadratic equation, 2 and 8 separation, minus, which means that this equation can be written as, okay, not x, t, the variable is t. T minus 2 and t minus 8 equals 0. Okay, so his t is 2 and 8. Of course, over there, when t equals 2, it is on the way up, and when t is 8, it's on the way down, right? Now, along with that, here we can find v, the velocity, v at 2, the same as 160 minus 32 times here 2. So there is a 64, so that is now 96. So it is coming up, okay. Now V8 is same as 160 minus 32 times now 8. So that is, that is, 160, and here, minus, and that is 2, right? 2 is 72, I believe, right? Okay, and oh, no, I'm sorry. Yeah, that is wrong. Okay, that is 6 and 256. So that is minus 96. Okay. So from here, the speed is the same. Absolute value of 96 is the same as now 96. But here, for that problem, the speed is 96. So speed is the same at time is 2 and 8, but on the way up, there's positive velocity, and on the way down is negative velocity. What is the acceleration of the rock at any time t during the flight? So acceleration can be gotten one more derivative from velocity, so that acceleration is same as v prime t, which is same as now minus 32. It's all the way just in downward. The acceleration is applied. It's constant acceleration. And when does rock hit the ground again? Okay. Once rock hit ground again, which means that S of t equals 0. Now, it is reaching at the highest when now t equals 5. This is quadratic function and symmetric, so that when t is 10, it should hit the ground. You can check it quite easily, that one. Okay, so we have to solve the problem S of t equals 0. Hit the ground means height is 0. That means that the function is now S of t is 160t minus 16t squared. Right here. Okay, 16t squared. That is now 0. Then divide by 16, and with multiplication of minus 1, we can reach that's t squared minus here 10t equals 0. That means that now t and t minus 10 equals 0, so that t equals 0 and 10. Okay, 0 means in the beginning it was on the ground, and after 10 seconds, and here up and down and hit the ground. Okay, so we can easily find it algebraically or geometrically. It's symmetric, so that we already know it reaches the highest position when t is 5. Then one more 5 seconds later, it will hit the ground. Okay. Now, at time t, the position of a body moving along the s-axis is given in this way. That is now quadratic polynomial of t. Find the body's acceleration each time the velocity is 0. Okay. Velocity is 0. At each time the velocity is 0. And we have to find the first velocity. So we want to find here body's acceleration at the moment the velocity is 0. Right? So okay, let's go here A. And velocity is same as derivative of the position. So that there's a 3t squared minus 6 times 2 is 12t, and plus 90, the derivative is 9. Okay, now a of t, that's one more time of derivative, is 60 minus 12. Okay, so the problem is asking, we want to find body's acceleration each time the velocity is 0. So that, okay, we have to solve the problem. Here, Vt equals 0, and we have to find the time when velocity is 0. That means that, okay, equals 0 divided by 3, we can get t squared minus 40 plus 3 equals 0, and 31 separation, so that we have here t equal 1 and 3. Okay, we have two moments, and when the velocity is 0. Okay, so here acceleration, we can find acceleration a1 equal 6 times 1 minus 12, which is now that minus x, and a of 3, which is same as 6 times 3 minus 12, which is now 6. Okay. Oops. Here, that is not a. In fact, that is 3. Okay. Okay. Now, part B, find the body's speed each time the acceleration is 0. So, part B means that under the condition that acceleration is 0, we have to find the body's speed. Acceleration is 0. The condition, that is 0, which means that already we have derivatives here. That one. So that 6t minus 12 equals 0, which means that t equal 2. So at the moment, acceleration is 0. Okay. And now, body's speed. First, we start with velocity, v at t equal 2. Then already we know v is here now. So there's 3 times 2 squared minus 12 times 2 plus 9. That is 12 minus 24 plus 9. So that is minus 3, which means that speed v at times 2 and absolute value is 3. Speed is 3. Okay. And finally, we want to find the total distance traveled by body from 0 to 2. Okay. And here, and looks like now from 0 to 2, the body is moving, for example, like, okay, it's moving in the beginning forward way, but as time passes, it's coming back. Then total distance is the distance from here to there and plus the distance from here to there. So 2, the position itself is not total distance traveled. We have to find part by part the distance and the sum, that is total distance traveled. Right? Here, now, and we already know that when time is 1, the velocity becomes 0, and now change the direction. And 3, and again, one more time, change the direction. So between 0 and 1, only now there's 1. That one is, when t is 1 is, the moment is changed. So that we have to measure, here total distance is the same as, basically, we have to, okay, in this line, okay, that is 2, from 0 to 2, t equal 0 to, we have to measure the distance, and we have to measure the distance, and we have the sum, that is 1 here, because at 1, it is changing the direction. Okay, when as t equals 0, it is 0, but when t equals 1, okay, so that S1, when t equals 1, now, okay, we write down the function here one more time. S of t equal, okay, now t cubed minus 6t squared plus 19. We write down one more time here, and we can see easily here. S is 1, S at 1 equal 1 minus 6 plus 9, which is the same as now 4. So at the moment here, S is now 4, okay? Now here at 2, okay, 2 cubed minus 6 times 2 squared and plus 18. So that is same as 8 plus 18 is 26 minus that is 24. So that is 2. Here, that is now moved to S equal 2. In position, here at 0, it is here. And when time is 1, is moving here at position 4. And when time is 2, then come back and here the position 2. So that total distance travel is the same as 4 plus 2 equals 6. Okay? Okay, now we'll go to the derivatives in economics and biology. In production, the marginal cost is just a derivative of the cost function. So once cost function is given in this way, then we can find the marginal cost by finding its derivative. Okay. Yeah. For this cost function, part A is asking you to find the average cost per machine of producing the first 100 washing machines. Okay, this cost function is for producing washing machines. Okay, once it is producing 100 washing machines, then total cost will be 100, C 100. Okay, there's now 2000 plus 100 times 100 and minus 0.1 times 100 squared. So that is now, okay, there's 10,000, so that 12,000 minus 1,000, so that 11,000. Okay, that is cost. Of course, it must be in dollar. But anyway, there's 11,000. Okay, and now here, the average cost is from this one, here you have to divide by 100, so that here C 100 divided by 100. That is the same as now 110 is the cost. Okay, the average cost. Now, marginal cost when 100 washing machines are produced. Okay, marginal cost can be obtained from derivative. So that C prime X, that is same as, okay, 2000 will be 0 in derivative, and that term will be 100 minus, and here twice, 2 times 0.1, so that is basically 0.2 times X. So here, from this one, C prime 100, when X is 100, so that is same as, okay, 100 minus 0.2 100, which is 20, so that will be 80. So the marginal cost is 80. Once marginal cost is smaller than the average cost, then you have to increase the number of production to maximize your cost. Okay, but anyway, for the problem, we can find C prime at 100 is 80. Now, in part C, the marginal cost also represents the approximate cost of the next item to be produced. And okay, show that the marginal cost when 100 washing machines are produced is approximately equal to the cost of producing one more washing machine after the first 100 have been made. And by calculating this cost directly, which means that here is we have to show that real practical marginal cost is around that one. So that, for example, now after 100 washing machines, one more, so that real marginal cost is basically C 101 minus C, okay, that is 100. Then we have to show that this is around 80, okay? So it is a little bit cumbersome computation, so rather than hand computation, let's try to use computer, okay? Now I open the Octave window, and for that one, I earlier defined the cost function. C equal now x is variable, and 2000 plus 100x minus 0.1 x squared. That is now the cost function. So here, let's try to measure, okay, C 101 minus now C, okay, not capital C, here 100. Let's measure that. Then that is here 79.9. So it's really about 80. Okay, you can check it quite easily. So that's the reason sometimes you need really a computer. Okay, quite easy. Okay, here. Now, bacteria side was added to nutrient broth in which bacteria were growing. The bacterium population continues to grow for a while, but later on it'll go down because of that, the drug. Okay, the size of a population at time t hours was given in this way. We want to find the growth rate at t equals 0, t is 5, and t is 10. Growth rate is just simply prime derivative, right? So here, that will be 0, and 10 to the 4. This derivative will be minus here 2 times 10 to 3, which is 2000, and t. So here b prime at 0 is 10 to the 4, which is 10,000. Now b prime at 5, which is 10 to the 4 minus here 2000 times 5, that is again 10,000, so that will be 0, and b prime at 10, which is 10 to the 4 minus 2000 times 10, which is 20,000, that means minus 10,000. Yeah, quite simple problem. Okay, now in this section, we'll solve the CAS problem, that is golf ball carrying. Okay, I organized this problem, and by solving this problem, you can understand that here, even though the problem is not considering ball spin and air resistance, but you can understand that why golf beginners here the longest with 6 iron and or 7 iron among irons. You can understand that. And I hope you enjoy solving this problem. A little bit complicated, however, anyway, and in this case, basically, compute wisely, you can do it. That is a sort of a vector, but here there's two components. If you make a derivative, then now here make a derivative for this component and derivative for that component. So it's compute wisely, you can handle the problem. Okay, that's the end of the section. Thank you.